We have two types of charge. What are they? Positive and negative, right? Easy question, right? Ridiculously easy question. Positive charge comes from having what? More protons than electrons, because protons are positive, right? And negative charge comes from having more electrons than protons, because electrons are negative, right? If we have a neutral object, then we have an equal number of protons and electrons. What's the charge of a proton, or an electron for that matter? Negative 1.60 times 10 to the minus 19. Remember on your data sheet for the charge, by the way, that's the symbol for charge. It's a lowercase q. The charge of an electron, on your data sheet, it says it's negative 1e. Negative 1 times the elementary charge, which is also given to you on your data sheet, as 1.6 times 10 to the minus 19. The charge of a proton, q, again, charge, q, of proton, is positive 1e, which means it's positive 1 times the elementary charge, 1.6 times 10 to the minus 19 coulombs. We talked about the size of a coulomb, right? We said that a coulomb is a really, really big unit of charge. It's so big that, in fact, you'd need about 10 to the 19 protons or about 10 to the 19 electrons to make up a full coulomb of charge. Because of that, because a coulomb is so big, we often see charge written not in coulombs, but we see it written in microcoulombs or nanocoulombs. We could see it written in other units as well, but these are probably the most common ones. A microcoulomb is what? Remember, we always got to convert back to coulombs. So we better make sure that we know what a microcoulomb is if we have to convert back to coulombs. 10 to the, don't remember that? That's okay. You check your data sheet. Check that data sheet right now. I believe it's the second page. It gives you all the SI prefixes, all the metric prefixes, or the SI prefixes. What's a microcoulomb? Yes, a micro, anything, is 10 to the minus 6. So a microcoulombs is 10 to the minus 6 coulombs. It's as simple as that. If you're given 65 microcoulombs, then just make it 65 times 10 to the minus 6. That's the easiest thing to do. A nanocoulomb, or a nano anything, is 10 to the minus 9. So if you have 12 nanocoulombs, then just make it 12 times 10 to the minus 9 coulombs when you do a calculation. Now, we haven't done any calculations yet this unit with this, other than that whole conservation of charge thing, balancing charges out. And there we don't have to worry about being in coulombs. We can be whatever we want. But today we're going to do something called Coulomb's Law, which does require us to do some calculations. And of course, because of that, does require us to be in our base unit of coulombs. Who remembers what a conductor is versus an insulator? Yep. Okay, conductor allows the electrons to flow. How come? Yep, Jesse? I'm sorry? Right. The electrons aren't as tightly bound to the nucleus in a conductor as they are an insulator. So therefore, they're more free to move about. They're more free to be transferred. What kind of things, what kind of materials tended to make the best conductors? Some better than others, obviously. But what general category makes the best conductors? Metals, right? And of course, things like nonmetals, things like plastic and wood and glass tend to make the best insulators. Good. We talked about the 3 laws of electric charge. There were 4 of them, really, right? But we differentiated between the first 3 and then the 4th one because they didn't really seem to fit together. What's the first one? Doesn't matter what order you give them to me, by the way. Opposite charges attract. So positive attracts negative. That includes opposite charged objects. A balloon that's positive will attract a piece of plastic that's negative. Okay? Positive objects will attract negative objects, but positive individual charges will also attract negative individual charges. Protons will attract electrons, right? Positive attracts negative, and negative attracts positive. What's the second one? Like charges repel. So positive objects repel positive objects. Negative charges, like electrons, repel negative charges, like electrons. What's the third one? Good. And it's important to mention the word objects there. Charged objects attract neutral objects. Protons don't attract neutrons. Electrons don't attract neutrons. But negatively charged objects do attract neutral objects. Can anybody explain to me why that's the case? Why do protons not attract neutrons, but yet positive objects do attract neutral objects? We talked about that a little bit yesterday, the reason for that. Yep. Good, good. Neutral objects have both positive and negative charges in there. That allows us to create a temporary separation of charge in a neutral object. And a temporary separation of charge is required in order to get attraction of a charged object in a neutral object. Now that doesn't happen if we just have a single neutron. You can't get a temporary separation of charge in a neutron, and therefore you can't get a positive object or a negative object being attracted to that single neutron. We'll talk a little bit more about why this neutral object is attracted to the charged object in a few minutes when we talk about the charging that we reviewed yesterday. All right. The fourth law, which doesn't really go with the first three, is the law of conservation of charge. That tells us the charge can't be created, it can't be destroyed. We've learned a couple of places now where that can kind of come into play. The first thing is charging by contact. When we touch two objects together, if they're different charges to begin with, let's say plus 5 and minus 12, then we know by the law of conservation of charge that after we touch them, although the charge is going to be redistributed, the charge is going to remain overall the same. Right now we have a charge here of minus 7 total. When we touch these two things together, it's still going to be minus 7, but they're going to be redistributed so that they balance out. What are they going to redistribute to become? Negative 3.5 and negative 3.5. Now, if you happen to have three charges, and you've got steps where charge 1 touches charge 2, then charge 1 touches charge 3, and then charge 2 touches charge 3, and so on, then make sure you do it separately in steps. You do this, and then do the next step, and then do the next step as necessary. The law of conservation of charge certainly applies there because we have to make sure that the total charge remains the same. Now, the other situation is when we talked about charging by friction yesterday. If we rub two objects that are neutral together, and one of them becomes negative 12, then the other object will become positive 12 because the total charge has to remain the same as it was before we rubbed them, which in this case was 0. So plus 12, negative 12 gives me 0. Hey, quick question about that, by the way. If you rub two objects together, one becomes positive 12 and one becomes neg 12, which one has gained electrons and which one has given up the electrons? It is electrons, by the way, that are gained and lost, right? Why is it electrons, not protons? Because the electrons are on the outside, and it's a lot easier for them to leave the atom than it is protons. Which one has gained protons? Which one has lost electrons? The plus 12 and the neg 12. Oliver? Good, good. The negative 12 has gained electrons. The positive 12 has lost electrons. Of course, if you lose negatives, you're going to become positive. If you gain negatives, then you're going to become negative, right? Yesterday we talked about two ways of charging objects. The first way was called charging by conduction. Good. And the second way was called charging by induction. You often see a word associated with induction, induce. Okay, when you see that word induce, you're inducing a charge. You're inducing something. Okay, that's referring to the second way of charging objects, induction. Okay, they're kind of synonymous, just a different way of saying it. Conduction always involves something and usually involves something else. Induction never involves something and never involves something else. Let's fill in the blanks here. Conduction always involves what? Charge transfer, yes. Conduction always involves a charge transfer. Conduction usually involves touching, although not always, right? We talked about a couple situations yesterday where it doesn't involve touching. When lightning strikes, electrons usually going from the cloud to the ground, although it can go the other way around, from the ground to the cloud. And when it goes one way or the other, electrons are moving. Electrons are being transferred either from the cloud to the ground or the ground to the cloud. That's conduction. because the electrons are being transferred. Okay, and that's the overriding factor that we use to determine whether it's conduction or induction. But the cloud and the ground aren't touching. They're just close enough that it allows the electrons to arc or jump from one to the other. The other example that we gave of that is when you walk across that carpet, shuffling your feet, and you go to touch somebody, but you shock them just before you make contact. That's still charging by conduction because charge is transferred, but it's we haven't actually made contact there. It's close enough that charges could jump, so it's still conduction, but it didn't actually involve touching. Usually, conduction involves touching, but not always. Induction never involves touching. Okay? If it's touching, it's not induction. And induction never involves a charge transfer. Good. Now, there were two subcategories of conduction that we had. We talked about those a little bit already today. We had charging by contact, which we sometimes just call charging by conduction, and we had charging by friction. Friction is the one we talked about first, actually, yesterday. Friction is when we just rub two objects together. Okay, one becomes positive, one becomes negative. Or if those two objects have charges that are different than neutral, they're not neutral to begin with, then one might become more positive and one might become less positive. Or one might become more negative and one might become less negative. Bottom line is total charge has to remain the same. All we're doing is transferring electrons from one of them to the other via the energy that's supplied by rubbing these two objects together. Charging by contact is what we've talked about for a couple of days now. When you touch two objects together that are different charges, they want to balance out. They obey the law of conservation of charge, keeping the same total charge. Charging by contact. Even if they don't actually touch, right, we still call it charging by contact. Induction, we had a temporary separation of charge, and then we had a permanent charge. We're going to review both of those real quickly here. Let's say we had a neutral object that is 3 protons and 3 electrons, or 3 billion protons and 3 billion electrons, or whatever, equal numbers. We bring a negatively charged object nearby. Tell me first of all what's going to happen to the protons in that neutral object. They're going to stay where they are. Nothing happens to them. Now, it is possible. Let's say that this object here that we have circled there is not a solid like we're normally assuming. Let's say it's a gas. And let's say it's not protons and electrons in there. Let's say it's positive and negative ions in there. It is possible for those positive ions to be attracted to the right-hand side. Right? Positive ions can move through a gas. But if we've got a solid here, and we've got atoms that are kind of fixed in place, more or less, in this solid, then we're not going to get the charges, the positive charges moving, because protons don't leave the atom. The electrons are the ones that move around. So where do the electrons go? If the protons stay where they are, where do the electrons go here? They're going to go to the far side. They're going to go further away, as far away from that negative object as they possibly can. Now we've got a separation of charge. The left side is negative, the right side is positive. But it's still temporary because as soon as I take that object away, they're going to go back to where they were before, more or less, so that it's evenly distributed. Okay, let's do another one here. Once again, we get an equal number of positives and negatives, but this time we're bringing a positive charged object nearby. What's going to happen to the negatives here? The protons, nothing happens, right? The protons stay where they are. What happens to the negatives? They're going to what, sorry? They're going to be attracted to it, and they're going to go to the right side. Still a neutral object, still overall 3 pluses, 3 minuses, but now we've got a separation where the left side is positive and the right side is negative. It's temporary because if we take this object away, it goes back to where it was. How do we make it permanent? We attach a ground wire. That ground wire can literally be a wire that goes into the ground, or it can be a wire that goes into some other really big object that can take the place of the ground, that can absorb as many electrons as you want or give as many electrons as you want. Or it can simply be any kind of conductor touching this object connecting it to the ground, or it can simply be a big, massive object that touches it. okay, that touches it and allows for all the electrons, as many electrons as we want to drain, or supplies as many electrons as we need to it. Bottom line is, whenever we have something connected to it that allows electrons to freely flow in or out, we call it grounding. Even if it's not technically attached to the Earth, we still call it grounding. What happens in this case over here? The electrons are going to go down, yeah. The electrons go as far away as they possibly can. So let's redraw this with these negative electrons going down here. Now we've got a positively charged object, but as soon as I take this away, it's going to go back to where it was. The electrons will just shoot back up that grounding wire into this now positive object and make it neutral again. How do I make it permanent? Cut the wire. Whoops, thought that was an eraser. Cut the wire before I take this away. Okay, same thing here, except that this time you're not pushing electrons down, you're pulling electrons up, giving you a whole bunch of extra electrons, making it negative. If we cut that wire before we take this away, then it's going to be left permanently negatively charged. Good? I told you a story yesterday about the fridge and the stove, and how we touched the fridge and the stove, we grounded the refrigerator and allowed electrons to flow through us, through the propane gas pipe into the ground. In that same house, I remember my 4th year, I bought a computer. In fact, it is, in 1994, this computer that you see at the back of the room right now, that had, get this, 4 megabytes of RAM, not 8 or 12 gigabytes of RAM. It had a 125 megabyte hard drive. I upgraded the monitor to a 17-inch monitor by paying an extra $200. The whole thing cost me $1,500 in 1994, which in today's dollars is more like about $4,000 for something that's not even as powerful as your calculators are today. Seriously, it's not. They're not. I had that computer. I bought that computer so that I could write my thesis, my senior thesis, at home, at my house, as opposed to going into the university and going on a computer there. So typing away, typing away, typing away. I had it for almost a month, and it died. $1,500 done for less than a month. Thankfully, it was under warranty. Here's why it happened. The hard drive in that computer, which is now taken out, the hard drive isn't in there anymore. The hard drive literally has a spinning disk inside, and they still do. They're much better now. They have much more capacity, and they're faster now, and they work a lot better now than they did then. But the technology, the basic technology is still the same. They have a spinning disk inside the hard drive. That spinning disk rubs against air and charges by friction. So we get a charge buildup on it. If your computer is grounded, then that's not a problem, because that charge buildup doesn't really occur and the electrons drain and it's all good. But if you don't have a grounded house, which of course we didn't, then what happens? You get a massive buildup of charge until it can't hold it anymore, and then what happens? It discharges, and then your hard drive is wrecked completely. So that's what happened less than 31 days after I bought my $1,500 computer in 1994. It was under warranty. I got a new hard drive. What did I do so that that wouldn't happen again? Hooked up to the stove. That's a good idea. I never thought of that. Although I thought of something that was close, and in fact, that's what I did. Not the stove, though. I literally just took, it's a simple fix, and I never had a problem with it again. I took a wire, just a regular copper wire, took one of the screws out of the back of the computer, and I screwed the one end of the copper wire into the back of the computer. So basically, the copper wire was touching metal on the computer. And then the other end, I duct taped the water pipe that was coming into the house. Simple as that. And that grounded my computer, and I never had another problem for the next 9 months that I lived in that house. Never had another problem with that computer because it was grounded. Easily grounded. It was grounded in a very easy way, but it has the same effect as that third prong. All right? Today, we're going to move on and do a little bit of math here. Today we're going to talk about a law called Coulombs Law. But before we do that, we're going to talk about where that law came from and how that law was derived. It comes from something called Coulomb's torsion balance experiment. Coulomb's torsion balance experiment looks something like this. This is a simplification. Okay, it really is a simplification, but it works for us. Attached to the top of a box is a little string. On the end of that string is a little rod. On the end of that rod, on both ends of that rod, are equal mass objects, objects that have the same mass, just so it's balanced out. One of those objects we're going to call Q1, charge 1. Now my fist, as I bring my fist close to this, my fist is going to represent Q2, charge 2. As I bring charge 2 nearby charge 1, depending upon whether they're both positive or one's negative, or they're both negative, we're going to get a force of attraction or repulsion. Charge 1 will either move towards charge 2, my fist, or it's going to move away from charge 2, my fist. We can measure the force here. We can measure, first of all, we can measure the distance that separates them. That's easy, right? We can use a ruler to measure the distance that separates charge 1 and charge 2. So we can get the value of, we're going to call it R, the distance that separates these two charges. We can also get the value of F, the force. And we can do that by using what we call the torsional properties of this string. You guys know that when you go on a swing set, sometimes you, especially when you were little, you would twist the swing set, right? So that you'd twist it as far as you could twist it, and then you'd let it go, and then you'd spin around really fast. You know that the more you twisted it, the harder it was to twist, right? Twisting means torsional, or torsional, I should say, means twisting. We use the twisting properties of the torsional properties of this string to measure the force. You could do an experiment with that swing set. It says, look, if I twist it 30 degrees, it requires this much force. If I twist it 60 degrees, I need this much force, and so on and so on and so on. If you do that experiment and you measure all these different angles and how much force is required to twist it that much, then you know the next time you twist your swing, simply by the amount that you twisted it, how much force was required to do that. Okay, we do the same thing here. We can determine how much force is required to twist a string a certain amount. When we bring a charge 2, my fist, nearby charge 1, and it twists 26 degrees, then we can look at that angle and say, oh, okay, it must have been this much force that was applied between these two charges. Does that make sense? So we can measure F. Now, Coulomb couldn't measure the value of charge. He didn't have a way of measuring Q1 or Q2, but he did have a way of measuring the relative charge, which was good enough for what he's trying to do here. He starts off with Q1 being, we'll just call it Q. The other one is 0. Well, nothing's going to happen there, or at least nothing experimentally valid is going to happen here. So what happens, we touch them both together. Now we don't have Q and 0. Now we have 0.5Q and 0.5Q. Then we touch one of them with a neutral object. Now we have 0.25 and 0.5. Then we can touch the 0.25 with another neutral object, and it becomes 0.125Q, and so on and so on and so on. So we don't know the actual value of charge in coulombs, but we do know the relative value of each of the charges, which is good enough. Coulomb is going to do 3 experiments here with multiple trials per experiment. In the first experiment, he's going to manipulate the value of Q1. If he's manipulating Q1, then it's going to appear on the x-axis of his graph. Responding to that will be F. The control variables there will be Q2 and R. In other words, you're changing the value of Q1, you're seeing what effect that has on F, you better make sure that Q2 and R stay the same. When he performs multiple trials of that experiment, he ends up getting a straight line. More or less, at least, a straight line graph. Well, then he does another experiment where he manipulates the value not of Q1, but of Q2. If you're going to manipulate Q2, you better make sure that Q1 and R stay the same. In other words, remain control variables. Plots that graph, and he gets another straight line. He does one final experiment with lots of trials. He manipulates the value of R. That's the distance that separates these two charges. For this one, he gets a graph that looks a little bit trickier. Gets a graph that looks like this. By the way, what does he got to keep constant if he's manipulating the value of R? Q1 and Q2. This experiment told him that F was directly related to Q1. This one told him that F is directly related to Q2. And this one told him that F is inversely related to the square of the distance that separates them. In other words, as R goes up, F goes down. As the separation distance increases, the force decreases, which makes some intuitive sense, right? The further the charges are away from each other, the weaker the force is going to be. The closer they are together, then the stronger the force is going to be. Now, when we combine these three experiments, F is related to Q1, F is related to Q2, F is related to the inverse of the square of the distance, we end up getting a single equation that we call Coulomb's law. F is related to Q1, Q2 over R squared. That's combining all three of those together. Now, if you remember from math class, when you deal with proportionalities, if F is proportional to Q1, Q2 over R squared, then it's equal to a constant times Q1, Q2 over R squared. That constant we're going to call K, Coulomb's constant. The value of Coulomb's constant is 8.99 times 10 to the 9 Newton meters squared per coulombs squared. Does this equation look a little bit familiar to you? You've never used this before, but you've used something that looks an awful lot like it. What is it, Oliver? Yes, Newton's law of universal gravitation. Newton's law of universal gravitation was G m1 m2 over R squared. The force of gravity between two masses related to the inverse square of the distance separating those masses. The electric force between two charges in coulombs divided by the square of the distance separating those two charges. Anybody remember the value for G, the gravitational constant here? Just one sec, Jay. Do you have a question, Jay, or an answer? Okay, one sec. Yep. Good, very good. 6.67 times 10 to the minus 11 Newton meters squared per kilograms squared. Now, the electric force and the gravitational force both take the same structure. We call them both inverse square laws because they're both inversely related to the square of the distance, inverse square laws. But one of them is normally a much bigger force than the other. As much as we think of gravity as being a big force, because that's the one we see every day. When we drop a pen, it falls to the ground. When we jump off the edge of a ledge, then we fall to the ground. We think of gravity as being a really big force. But in reality, it isn't. Gravity is a minuscule force compared to other fundamental forces. It's very, very small. And we can tell that by looking at the constant. This is 10 to the minus 11 for the gravitational constant. And Coulomb's constant is 10 to the positive 9. It's 10 to the 20 times bigger. Okay, all other things being equal, the electric force will be much bigger than the gravitational force because the constant is so much larger. All right? Jade, you had a question? What is this one here? That just means proportional. That means related to. So F is related to Q1, Q2 over R squared, but it's not equal to Q1, Q2 over R squared. It's related to it. To make it equal, we have to put in a constant. And that constant happens to be 8.99 times 10 to the 9. This is just a quick little comparison of Coulomb's law with Newton's law of gravitation that we learned in Physics 20. The relationship, they're both inverse square relationships because they're both have the force related to the inverse of the square of the distance that separates the two objects, whether they be masses or charges. Magnitude? Well, Coulomb's law is a really big force. And it's a big force because it has a constant that's in that range of 10 to the 9 versus gravity, which is a small force in the grand scheme of things, has a constant that's 10 to the minus 11. And in terms of direction, well, of course, gravity, as far as we know, has to always be an attractive force. Okay, we're not aware yet of gravity ever being a repulsive force. But Coulomb's law, the electric force, as you know, we learned this the very first day of this unit, right? It can be attractive or repulsive depending upon what kind of charge you have. I mean, think about that, right? We can have two types of charge, positive and negative. That's why we can have both attractive and repulsive. Gravity, there's only one kind of mass. So because there's only one kind of mass, you can't have both attractive and a repulsive force. Let's take a quick look at an example here. So it says a small metal sphere with a negative charge, I'm probably going to circle that because I'll probably forget to put a negative in front of it if I don't. Of 2.1 times 10 to the minus 6 is brought near, that's by the way 2.1 microcoulombs, right? Brought near an identical sphere with a positive charge of 1.5 times 10 to the minus 6 coulombs. Distance between the centers is 3.30 centimeters. I definitely want to draw attention to that. What's the magnitude and the type of force that we have there? We're going to call this Q1. We're going to call this Q2. We're going to call this R, and we want to find F. The magnitude of the force, first of all. It's going to be K, Q1, Q2 over R squared. K is 8.99 times 10 to the 9 times, notice what I'm doing here? As much as I said, make sure you circle that negative to make sure that you draw attention to that. I'm not plugging it into this equation. We never plug the sign of a charge into an equation. For us, negative will mean a direction, not a type of charge. In a math equation, we're going to need to know that this is a negative charge a little bit later on in determining whether it's attractive or repulsive. But we don't need to know whether it's a negative or positive charge in determining the magnitude of the force. So don't ever plug a negative into the equation. We'll use it later on to determine whether it's attractive or repulsive. Let's divide that by the distance, and let's make sure that we do convert that. 0.330 meters squared. Let's do the math on that. We'll pull up our calculator and do that together this time. Let's say 8.99 times 10 to the 9. I don't think I'm aligned here. There we go. 8.99 times 10 to the 9 times 2.1 times 10 to the minus 6 times 1.5 times 10 to the minus 6. Let's press equals on the top there. And let's divide it by, use some brackets because we've got to square that on the bottom. 0.033 squared, and the bracket. We get a force here of 26 newtons. That's the magnitude of the force. Notice the absolute value signs. That tells me that that equation is only ever going to get me the magnitude, not the direction. What about the direction? Is it attractive or repulsive? We've got a positive and we've got a negative. It's going to be an attractive force. The equation doesn't tell me that. Simply by virtue of the fact that one's positive and negative, I can determine that it's an attractive force. I'm sorry. I get the attractive by looking at the types of charges. A positive and a negative, we know attract each other. If they were both positive, then the magnitude of the force would be exactly the same, 26 newtons, but it would be a repulsive force. Or if it was two negatives, again, 26 newtons, but it would be a repulsive force. All right, here's your homework for the weekend. I'd like you to do, please, page 523, questions 7 to 10. Page 523, number 7 to 10. Those are some check and reflect questions just on general electrostatic stuff, not Coulomb's law. In addition, I'd like you to do page 530. That's this practice problem right there. Page 530, number 1. What the heck? What is that? 4 questions? 4 questions? What the heck? Let's do worksheet number 6 that I'm going to give you here in just a second. These are going to go really, really quickly for you, so that's why I don't mind assigning 7 or 8 questions here. Worksheet number 6, questions 1 to 4. What the heck? While we're at it, let's just, no, that's it. That's it. That's assigned for Monday. This is the stuff that's good for your quiz on Monday. So take a look at that and then ask me Monday morning real quickly before we do our quiz if you have any trouble with that. And then this stuff, these 5 questions are on the stuff that we did today. All right, that's it for today.